I'm Zor. Welcome to Unizor Education. Today's topic will be induction, mathematical induction. Induction is a method you can use to prove certain formulas. And let me start from a very simple problem and how this particular method is applied to this. There is a legend about German mathematician Carl Friedrich Gauss. When he was a child, apparently teacher asked the class where he was to add numbers from 1 to 100. Well, maybe the teacher wanted students to keep quiet for a while, so it would take them a while to add all these numbers. Quite suddenly, the teacher saw that young Carl raises his hand and basically gives the right answer. Apparently what he did was he noticed that if you will take this sequence of numbers and write it backwards, 100, 99, 98 plus 1. Well, basically you have exactly the same sum of numbers, and if you add them all together, it will be double the sum which was originally supposed to be calculated. But if you instead add it vertically using these pairs first, he noticed that the sum of these is 101, the sum of these will be 101, 3 and 98 is 101, etc. And the last one will be 101. And how many times 101 participates in this sum? Well, obviously 100 times. Well, using the multiplication, the total sum will be 10,100. But then again, this is a double of the original sum. So what we are looking for is half of this number, which is 5,050. And that's the answer Gauss did. Well, that's the right answer. Now let's try to generalize it a little bit. Instead of adding numbers from 1 to 100, we will use the same methodology young Carl Gauss was using, and let's try to add numbers from 1 to any arbitrary number n. Well, we'll do exactly the same thing Carl did. He was a genius, by the way. Let's write them backwards. And again, sum of all these numbers is double the sum which we are looking for. But instead of summing it horizontally, we will sum in this direction vertically and then multiply, obviously. And as you understand, the sum of these is n plus 1. Sum of 2 and n minus 1 is, again, n plus 1, etc. And sum of these two is also n plus 1. Exactly the same logic. N plus 1 participates n times. So the total will be n times n plus 1. And since this is double of the whole sum which we are looking for, the real answer is this. This is the formula. Okay, fine. Let's write it down again. 1 plus 2 plus etc. plus n equals. This is a nice formula. So whenever we want to calculate sum of numbers from 1 to 1,000, let's say, we can use the formula. It's 1,000 times 1,001 divided by 2, whatever it is, very easy to calculate. Great. Now, can we really use this formula for any n? Well, we didn't prove it for any n. We kind of guessed that this will be exactly the sum. We basically noticed that there is a vertical sum of n plus 1 in each pair of vertical numbers, but then it's really a guess that it will be exactly the same for all these intermediate members as well. And we cannot obviously check that this particular vertical sum will be equal to n plus 1 for each number. We just did it for a couple of numbers in the beginning and a couple of numbers at the end, and that's it. So, mathematically speaking, this is not a rigorous proof. And the method of mathematical induction is exactly this rigorous proof. This is the method we can prove the formula is really valid for any n. Now, here is the method, how it's supposed to be used in a rigorous sense, so to speak. This method contains actually 3 steps. Step number 1. Check for n equals to 1. So we have to check this formula for some initial number. Usually it's number 1, for instance. Well, for number 1, the sum on the left will be from 1 to 1, which is 1. And the number on the right will be 1 times 1 plus 1, 2, divided by 2, also 1. So 1 equals 1, formula checked. Okay, we definitely know that this formula is valid for certain initial number. In this case, it's number 1. Number 2, assume, and this is a very important word, assume that the formula is valid for some number n equals to k, where k is any number, whatever we want. So let's assume for a second that one plus 2 plus etc. plus k equals to k, the k plus 1 divided by 2. Now, this is an assumption. We are not saying this is the truth. We are assuming that this is true. And based on this assumption, number 3 is let's prove it for n equals k plus 1. So let's assume that the formula is true for n equals k, and using this, let's prove that the formula is true for n equals k plus 1. So let's assume that if we will add k numbers from 1 to k together, we will get this number. Now, let's add k plus 1 numbers. What happens in this case? Well, let's calculate now. If you take numbers from 1 to k plus 1, it will be 1 plus 2 plus etc. plus k plus 1. This is the sum which we are trying to prove is equal to the same formula, but with n is equals to k plus 1. Okay, let's do it. Now, using our assumption that the formula is true for n equals k, instead of this sum from 1 to k, we can write k times k plus 1 divided by 2. So this is our expression now. Okay? This is exactly where we're using this assumption. Now, let's just change it a little bit. It's k plus 1, 2, plus 2, k plus 1 divided by 2. So instead of k plus 1, I multiply and divide it by 2. So we'll have a common denominator. So k plus 1 can be factored out. K plus 2 remains. Divided by 2. Okay. So using our assumption, that's extremely important, we have come up that this particular sum from 1 to k plus 1 is equal to this. Now, let's think again what we are trying to prove. We're trying to prove that n plus 1 plus 2 plus etc. plus n equals to n times n plus 1 divided by 2. We're trying to prove that this formula is valid for any n. We have assumed that for n equals k it's true. Now, how does this formula look for n equals to k plus 1? Well, on the left it will be 1 plus 2, etc. plus k plus 1, which is this. On the right, if n is equal to k plus 1, n is equal to k plus 1. n plus 1 is obviously k plus 2 now. So, n divided by 2. So, this formula with n equals to k plus 1 is exactly what we have just received. Sum from 1 to k plus 1 on the left, and k plus 1 times k plus 2 divided by 2 on the right. So, again, what we have done, we have proved that the formula is true for n is equal to k plus 1, assuming that the formula is true for n equals k. Where the assumption was used, again, whenever we broke this sum into two components, the left one, where we can use an assumption, plus the right one, the k plus 1, which is kind of a small one, then after small transformations, we came to this thing. So basically, we made all these three steps. Okay, is that the end of it? Well, obviously not. We have to say something to basically prove that the formula is true for any number. How can, from these three steps, we can derive that the formula is true for any number? Very simply. Formula is checked for n is equal to 1, right? We definitely know it's true. Then, here is the assumption: if formula is true for n equals k, then the formula is true for n is equal to k plus 1. Great, but we know that for k is equal to 1, formula is true. We checked it. All right. So first step is k equals to 1, and we use this transformation. If it's true for k, it's true for k plus 1, which means if it's true for k equals 1, it's true for k equals to 2, k plus 1, right? Great, so we basically proved that the formula is true for sum of two numbers. Okay, since it's true for 2, again, using this transformation from k to k plus 1, where k is equal to 2, what follows is that the formula is true for k is equal to 3. And obviously this process can be continued indefinitely, and for any number, any natural number, 100 million or whatever, using this logic, step by step, from 1 to 2, from 2 to 3, from 1 million to 1.5 million, we are actually making these logical assumptions, and therefore it proves that it will be true for any number. Because for any number, we can repeat these steps whatever number of times we want, starting from 1 up to that particular number, and the whole thing will be proven. Again, what's very important is number 1, we checked it for some initial number, usually 1, then the formula can be assumed for a certain number. Let's assume it's true for k. Then, using this, we proved it that the formula is true for k plus 1. Right. Okay, so this is the methodology. And what probably is seems to be as a very important step is this step, because we spent basically most of the time proving that if the formula is true for n is equal to k, then the formula is true for k plus 1. Now, the fact that we have spent a little bit more time on this than checking that the formula is true for the beginning, for the initial number 1, doesn't mean that this is unimportant. Actually, if the first step is not made, then we cannot make the first and then all subsequent, obviously, steps in this logical stepping. So it's very important to check that the formula is true for the initial value of n. Usually it's 1. Now, if we don't do this, if we just make the proof that if some formula is true for n is equal to k, then it will be true for n equals k plus 1. If we just make this logical step, it doesn't prove anything without this checking. As a matter of fact, you can prove a lot of absolutely wrong formulas using this methodology. And again, since it's not checked for the beginning, for the n is equal to 1, then this logical transformation from assumption to the proof doesn't really mean anything at all, because you can't use it. Here is an example. Let me just make a little bit more space. What I would like to explain right now is that this transformation from step 2 to step 3, from assumption that the formula is true for n is equal to 1 to prove that it's equal to n plus 1 is not sufficient. Here's my formula. N equals n plus 1 for any n. Obviously the wrong formula. Alright, but let's try to prove it using the method of mathematical induction. And what's very important, again, the number 1 step, check that the formula is true for some initial number, let's say for n is equal to 1. Let's say we do not do this. Obviously, if you put 1, it will be 1 is equal to 2. It's definitely wrong. So the whole method of mathematical induction is not fully implemented. However, step 2, assume that k is equal to k plus 1 for some k. Now, prove for k plus 1. All right. Let's n to be k plus 1. On the left, we will have k. Using assumption, we will substitute it to this. We will see that k plus 1, using this assumption, plus 1, which is equal to k plus 2, which is exactly our formula for k is equal to k plus 1. K plus 1, k plus 2. That's exactly what we have proved. K plus 1, k plus 2. So using this assumption, we have proved basically the transformation from k to k plus 1. So obviously, using just these two steps, assumption for n is equal to k and proving that the formula is also valid for n is equal to k plus 1, this works. But again, without the checking, it's absolutely worthless. We can't really say anything because logical transformation is based on steps from 1 to 2, from 2 to 3, etc. So the initial step, like 1 for instance in this case, is extremely important. Well, basically that concludes explanation of what is method of mathematical induction is. And there are a few problems which I have also put on this page, and you definitely are invited to click on these and try to solve them yourself, and if not, just look at my explanation of what these particular problems are about and how to solve them. Thank you. I'm Zor. Welcome to Unizor Education. This is a continuation of the topic on mathematical induction. We'll talk about some problems. So this is the first problem. Okay, here is the first problem. And we will use the method of mathematical induction to prove some very interesting formula. Look at the following. If you have number 1 and you square number 1, you will get 1. If you will get a sum of 1 and 3, the number of these members in this sum is 2, and if you will square 2, it will be 4. And if you notice, this is 4. Okay? Let's take the next odd number, 1, 3, and 5. It's 9. Number of these members in the sum is 3, and 3 squared is 9 again. Well, is this a coincidence? Well, definitely not. And here is what we are trying to prove. That if we will have certain number of odd numbers added together, then the sum will be equal to the number of these numbers squared. And here's how to express it mathematically. If you have 1 plus 3 plus 5 plus 7, etc. This is member number 1, this is member number 2, this is member number 3, this is member number 4. So this is a number of the member of our sum. How can we connect the number of this member and its value? 1 and 1, 2 and 3, 3 and 5, 4 and 7. So how can we say that the number 4 in this sequence of odd numbers is 7? Well, that's actually quite simply. It's 2 times n minus 1. This is a general formula for nth odd number. If n is equal to 1, the first number is 1. If n is equal to 2, 2 times 2, 4 minus 1 is 3. If n is equal to 3, 3 times 2, 6 minus 1, 5. And if n is equal to 4, 4 times 2 is 8 minus 1, 7. So this is the generalized formula which gives you the nth odd number. So what I'm trying to prove is that if I will have first n odd numbers and add them together, so the nth will be 2 times n minus 1. This is number n. Okay? So if I will have n odd numbers and sum them together, I will try to prove that this is n squared. Well, this is not really obvious. I mean, we did check it in a couple of initial cases. And how can we prove this formula in the general case? Well, obviously the method of mathematical induction is very handy in this case. That's why I'm presenting this as a problem. I think this is a very good position right now to basically pause the video and try to solve this problem just by yourself. So just press the pause button, think about this particular problem, and then play it again. So whatever I'm trying to put right now is basically an explanation and solution to this particular problem. Would be interesting if you first try it and then check it against whatever I'm trying to prove. All right, so now we will have a solution to this problem after you paused and tried it yourself, obviously. All right, so this is the problem. This is the formula which we are trying to prove. Okay, if you remember, the method of mathematical induction consists of 3 steps. Step number 1, we check for n is equal to 1. Well, let's check it. For n is equal to 1, I'm supposed to have only one member on the left. N times 2 is 2 minus 1 is 1, so this is the generalized expression for the first member only. So n is equal to 1. On the left I have 1. On the right I have 1 square, which is 1. Checks. Fine, no problem. Now, let's assume that 1 plus 2 plus etc. plus 2 times certain number k minus 1 is equal to k squared. Let's assume this is true for some particular k. And we have to prove, using this of course, that 1 plus 2 plus etc. plus the one before last member will be this, and if instead of n I will put k plus 1, let's think what will be k plus 1 times 2 minus 1. This is my formula, this is my sum on the left with k plus 1 members. Okay, let's transform it. Since we know that this piece, by assumption, is equal to k squared, we can say that the whole sum is equal to k squared plus, and let me just make it a little simpler, 2k plus 2 minus 1, it will be 2k plus 1. Right? 2k plus 2 minus 1. It's 2k plus 1. Now, great. This is, by the way, k plus 1 squared. If you don't believe me, just check it out yourself. This is the formula for k plus 1 squared. No, indeed, for those who... Okay, I will check it for you. K squared is k plus 1 times k plus 1, which is k times k, k squared. K times 1 is k. 1 times k is k. And 1 times 1 is 1. And this is 2k. 2k. K squared plus 2k plus 1. All right. So what it looks like that using an assumption for n is equal to k, I have proved that basically this formula, you see this k plus 1 squared, that's exactly what it is. That the formula is true for n is equal to k plus 1. So all 3 steps of mathematical induction are performed, validated, everything is fine. So the whole thing therefore is proven. So we have proved that for any n, this formula is true. Let me again repeat these logical steps which have to be just said about this proof. Since we have checked it for 1, and we also assuming that the formula is true for some number k, it will be true for number k plus 1, we can really make a conclusion that since we checked for 1, for k equals 1, then it will be true for 2. We make a transformation from k to k plus 1. So from 1 we can make a transformation to 2. From 2 to 3, from 3 to 4, etc. So any number of odd numbers, sequential number of sequential odd numbers added together, if their number is n, then it will be n squared as a sum. That's a complete proof. Thank you very much. I'm Zor. Welcome to Unizor Education. Today's topic is a problem for mathematical induction. This will be problem number 2. Okay, so here is the problem. Before we were talking about certain algebraic formulas, like left part is equal to right part, for instance, sum from 1 to n is equal to whatever the expression was on the right, and we were trying to prove this equality using the method of mathematical induction. Not only these equalities can be proven. This problem will be about inequality. I would like to prove an inequality of the following type: that n factorial is greater than 2 to the power of n. Now, by the way, n factorial is 1 times 2 times 3, etc. times n. And obviously, 2 to the power of n is 2 times 2 times 2. N times, and this is also n numbers from 1 to n. So the multiplication of n numbers from 1 to n is greater than multiplication of numbers of n times repeated number 2. Okay, so this is the problem, and I would like you to prove it using the method of mathematical induction. By the way, let me just give you a little hint. If you will start checking this formula for n is equal to 1, or even 2, or even 3, it will be wrong. But basically you feel that the more numbers on the left, the bigger the number n is, we are multiplying by a bigger and bigger number. So this thing is growing quite fast. This thing is growing with the same speed. It's always times 2. So eventually this number should be greater than this number. We all feel this type. However, for initial number 1, 2, or even 3, this is not true. So the hint is that the first step in the mathematical induction, which is checking the formula for a certain specific initial value, this initial value should not be 1 in this case. It should be greater than 1. Actually, it's 4 or 5 or something. Because this formula, which we would like to prove, is supposed to be valid for big number n's. Any big number bigger than something. So this is the problem. Prove this formula for n greater or equal than 4. So 4 becomes your initial value. Perfect spot to pause the video and think about this yourself. Try to prove this inequality using the method of mathematical induction, and then you can click the play button again, and I will continue with solution to this problem. Okay, so mathematical induction, 3 steps. Step number 1, check. For n equals to 4. Okay, for n equals 4, n factorial equals 1 times 2 times 3 times 4 equals to 24. 2 times n equals 2. 2 to the 4th degree, which is 16. Obviously, 24 is greater than 16, so the formula is true for n equals to 4. Checked. Step number 2. Assume for n equals to k. Okay, so we assume that k factorial is greater than 2 to the kth degree. 3. Let n equals to k plus 1. We have to prove that the formula is true for n is equal to k plus 1. On the left, we will have k plus 1 factorial. Formula with n equals to k plus 1 is k plus 1 factorial. What is k plus 1 factorial? It's 1 times 2 times etc. times k and times k plus 1. Right? That's what k plus 1 factorial is by definition. Now, notice that these multiplied together give you k factorial. So k plus 1 factorial is actually a k factorial times k plus 1. Now we can use our assumption. This is our assumption. That k factorial is greater than 2 to the k's. Greater than, so instead of k factorial, you put 2 to the power of k times k plus 1. Now, k is at least greater than 4, right? So k plus 1 is definitely greater than 2. So it's greater than 2 to the k's times 2, which is equal to 2 to the power of k. Basically we have, sorry, k plus 1. K plus 1. So that's what we have proven, that the k plus 1 factorial is greater, equal, greater, and greater again, than 2 to the k plus 1. That's it. So we checked, we assumed for n is equal to k, and then we prove that for n equal to k plus 1, this formula, this inequality is valid. And now again, we don't write it down, but we always say it, or at least we think about this, that considering we checked that the formula is true for n equals to 4, and considering that we can step always from k to k plus 1, therefore we can step from n is equal to 4 to n is equal to 5. Because our assumption is based on n is equal to 4, and from this assumption we proved that it's true for k plus 1, so therefore we proved for n equal to 5. From 5 to 6, from 6 to 7, etc. So the formula is true for any n greater than 4, up to infinity. Well, that concludes this problem number 2. Thank you. I'm Zor. Welcome to Unizor Education. I will present problem number 3 in for mathematical induction. Here's the problem. Let's assume you have certain number of lines on the plane. And we will assume that there are no parallel lines, and there are no lines which cross, no more than 2 lines are crossing in any particular point. So I am excluding this case when there are parallel lines, and I'm excluding case when 3 lines are crossing in exactly the same point. So this is not happening. We have only non-parallel lines which are with crossings of no more than 2 lines in any point. Question is, how many cross points we have in case of n lines? Well, in case of 1 line, obviously we have no crossing. In case of 2 lines, obviously we have only 1 crossing, right? 2 lines are crossing in only 1 point. No parallels. Okay. In case of 3 lines, so this is n and this is cross. In case of 3 lines, as you see here, we have 3 crossings. Well, let's just go on. In case of 4, well, 4 actually does something like this, right? It's not parallel to anything, which means it's crossing anything. I added 1, 2, 3 points, so I have 6. So these are my sequences. It looks like the formula should be very easy, and I'll just give it to you, and you will try to prove it. The formula is n times n minus 1 divided by 2. Let's check it. For 1, it's 0, because this is 0. For 2, this is 2, this is 1, divided by 2, it's 1. For 3, 3 times 2 divided by 2, it's 3. And for 4, 4 times 3, 12 divided by 2, 6. Alright, so that seems to be like the right formula. Okay, try to prove it using the method of mathematical induction. Press the pause button and do it yourself. And I will try to prove it here. Okay, so the formula is n lines, no parallels, and cross 2 lines only. No 3 lines are crossing at the same point. And the formula which I would like to prove is that the number of crossing points is this. Alright, let's go through the steps. Step number 1, check. Well, we have already checked for 1, 2, and 3. Formula actually holds, so the check is fine. Let's say for n is equal to 1. For 1 line. The formula is 0, no crossings because there's only 1 line. We did that. Okay. Assume, what do we assume? That n lines of that type cross in, sorry, let's do it this way. K lines. I don't want to use n anymore. Let's assume that n is equal to k. So we have k lines are crossing in k times k minus 1 divided by 2 points. And 3, we have to check that the formula is correct for n is equal to k plus 1. So let's just draw another line. We have k lines, we draw another line. As I said, no parallel lines, which means this new line will cross each and every one of those old lines. Now, all these crossings will be new because no old cross points should be crossed again, because I said no more than 2 lines are crossing in the same point. So whenever we draw the next line, the k plus first line, it crosses all the old lines, which means it introduces new k points of crossing. So when I have n equals to k plus 1, I actually add k points, crossing points. Well, let's see if our formula will be held in this particular case. So we assume that k lines by themselves are crossing in k times k plus minus 1 divided by 2 lines. I introduced k new points. And how the formula will look? Well, that's easy. It's k times k minus 1 plus 2k divided by 2 equals, okay, let's factor out k, and what will be? Will be k minus 1 plus 2, which is k plus 1, divided by 2. Now, let me just rewrite this formula slightly differently. Since I need space, I will wipe out this. Instead of k, I will use k plus 1 minus 1. That's the same thing, right? So, I assume that my formula for n equals to k looks like this. And for n equals to k plus 1, we derived that the formula looks like this. But as you see, this is exactly the same formula, right? K plus 1, this is, instead of n, we put k plus 1. So the formula looks exactly the same way. It's number n, whatever the n is in this case it's k plus 1, in this case it's k. Same number n, minus 1. So the formula is exactly the same. So for n is equal to k, it's this one, and for n is equal to k plus 1, formula has exactly the same form and shape. So the formula holds, and that actually proves the whole point. So if you have n lines on the plane, they cross under these conditions, obviously no parallels and no more than 2 lines are crossing at the same point. So they cross each other in n times n minus 1 divided by 2 points. And now here is an interesting thing. If you remember, if you looked at the lecture which we started mathematical induction with, we started with a summation example which young Carl Gauss, when he was 7 years old, he added up numbers from 1 to 100. And obviously, what happens with lines on the plane is exactly the same as what happens with numbers if you are adding numbers from 1 to n. Why? Because each new crossing is introducing the next number in this summation. So if you have one line, you have 0 crossing. If you have 2 lines, it introduces crossing with old lines. If you have 3 lines, it introduces new 2 crossings with old 2 lines. If you have 4 lines, it introduces 3 new crossings with 3 new lines. So as you see, this is exactly the same thing. So if you have n, that's n minus 1 actually. So the number of crossings, if you have n lines, is a sum from this to this. And that would be exactly the same formula. Okay, that basically concludes this problem number 3. Thank you very much. I'm Zor. Welcome to Unizor Education. I would like to present problem number 4 in the area of mathematical induction. As the previous problem number 3, this will be about geometry. Okay, let's consider you have a polygon. The shape of this polygon, it should be like this. I don't want to have something like this. No such thing, right? I think it's called convex. Question is, if you will summarize these angles, internal angles of this convex polygon, what will be the sum of these angles? Now, in case of a triangle, everybody knows that the sum of internal angles of triangle is 180 degrees. I'm not going to prove it, by the way. I'm just taking it for granted. This is school math. Okay, so the question is, what's the sum of internal angles of this polygon? Well, again, let's start with some kind of an analysis of this situation and do it step by step. Let's say you have a 4-sided polygon. Well, obviously, I can divide it in 2 triangles. Sum of these angles is 180, and sum of these angles is 180. So it looks like we double 180. So for triangle, we have 180. For a polygon with 4 sides, it looks like it's 360. Okay, fine. Let's do a 5-sided polygon. Well, it's very easy. Again, cut this triangle out. This is 180. Sum of these 3 angles. And this is a polygon with 4 sides, which we have already know. Alright, so it looks like we have added another 180. So for n is equal to 5, it will be 540. So it looks like every time we are adding a triangle, we are adding another 180 degrees, right? So basically this is the basis of the proof using the full mathematical induction, which I'm going to introduce right now. So the formula seems to be 180 degree times n minus 2, where n is number of sides of the polygon. For 3, it's 180, 3 minus 2 is 1. For 4, it will be 4 minus 2, 2 times 180, 360, etc. Alright, so this is the formula, and how do I prove it? Well, again, number 1 step for n equals to 3, we have already proved, we know it, it's school math, it's 180, formula is holding fine. Number 2, let's assume that if n equals to k, if we have a k-sided polygon, the formula is 180 degree times k minus 2. And let's think about what happens when we have a k plus 1-sided polygon. Well, as I said, if this is a convex polygon, it means I can always take 3 vertices and cut a triangle out of it completely. So this will be a polygon with k sides, right? Because I just cut out 1 vertices and replaced 2 sides with 1. So I cut down the number of sides by 1. So now I have a inside of this side, this is a k-sided polygon. And I know that the formula for all these angles is 180 times k minus 2 by our assumption, which is number 2. And what do I add? I add these 3 angles of a triangle, which is always 180, so I have to add 180. And what will be? Well, obviously it will be 180 k minus 1, which is 180 k plus 1 minus 2, because that would correspond this minus number k plus 1 and this number k plus 1. So the formula is exactly the same. I substituted n with k plus 1 here, with k there. Formula is exactly the same, so formula holds, and that basically proves this fact that for any n-sided convex polygon, the sum of all internal angles is 180 times n minus 2. That concludes it. Thank you very much. Hello, I'm Zor. Welcome to Unizor Education. Today's topic will be induction, a problem in the category of induction, problem number 5. And in this particular case, it's a real problem. It's much more difficult than those little exercises we did before. So let me go straight to the point. This is actually a theorem which was attributed to French mathematician Cauchy. Here it goes. First of all, there are two definitions: the arithmetic average and geometric average. Now, arithmetic average of n numbers is, as you know, their sum divided by their number. The geometric average of the same numbers is an nth root of their product. Well, intuitively, it is kind of obvious that both averages are really average. They are somewhere in between these numbers. However, they are quite different, and there is a famous inequality between these two averages. Arithmetic average is always greater or equal than geometric average of n positive numbers. We'll talk about positive numbers just because we don't want to have something like a square root of negative numbers or whatever. So all numbers are positive, and arithmetic is greater or equal than geometric average. The problem number 1 is, let's prove it. Well, first of all, let's start from a simple case. Only two variables. And we will try to prove it for this case when n is equal to 2. So we have to prove that x1 plus x2 divided by 2, that's average of two numbers, is greater than square root of their product. So this is the arithmetic average, this is the geometric average. Well, this is actually quite simple because if you will take this obvious inequality, since this is the square root of x1 minus square root of x2. Now this is obvious because this is a square, so every number, positive or negative, being squared will give a non-negative result. But if you will open this, you will see that this is square of the first, which is x1, minus 2 product, plus square of the second, which is x2, and that's greater than equal to 0, which basically gives us this inequality. This goes to the right, so we'll have x1 plus x2 greater than 2. Now, the multiplication, this product of two square roots is obviously square root of their multiplication. That's the property of the power. And this is the same as this, that just divide by 2. So, in case n is equal to 2, it's really very simple thing, straightforward check, and there is no problem. Now, obviously, since I started the whole problem in the category of induction, we will try to prove the whole thing using the method of mathematical induction. So we have proved for one particular beginning value of n, and a typical way of proving something using the method of mathematical induction is, well, first you check it for some beginning number, like for instance n equals to 2, and then you prove a theorem, assuming that the formula or an equality or whatever is true for n is equal to k. Assuming that that is true, prove that it will be true for n is equal to k plus 1. Then, using the standard logic from n equals to 2, using this theorem, we go to n equal to 3, from 3 to 4, etc., and that's how we prove it for any finite number. In this particular case, it's not that easy. Because if you will go to a 3, for instance, and you have to prove this, the third root of n x1, x2, x3. Now, it's not really obvious how from this we can go to this. However, let's make another observation. If I will use n is equal to 4 instead, so I have 4 numbers, and I have to prove that this is the fourth root of their product. This actually is quite easily deducible from the previous one. How? Well, very simply. Just divide it by 2 pairs. So it will be x1 plus x2 divided by 2, x3 plus x4 divided by 2, and divided by 2. Now, obviously, this left part is the same as this one, right? The common denominator 2, so it's the sum of these 4 divided by 2 and divided by 2 more, so it's divided by 4. Now, but this, let's consider this as a one number and this another number. And we know that their arithmetic average, just 2 numbers, we will use this thing, is greater or equal than square root of their product. Right? So these are individual numbers. And I'm using my theorem, which I have actually proved for n equals to 2. In this case, it's one number, two numbers, their average greater than their arithmetic average is greater than their geometric average. Now, in turn, I can say that this is greater or equal than. Now let's consider just these 2 arithmetic averages and use this same theorem. So it will be square root of x1, x2 times square root of x3 times x4. Now, obviously, square root of square root is the fourth root, right? So this will be the fourth root of x1, x2, x3, x4. And that's exactly what we had to prove from the very beginning. So, we have switched from 2 to 4 elements, from n equal to 2 to n equal to 4, very easily. We just divided by pairs. Now, if I will have, instead of 4, if I will have 8 numbers, how that would be? Well, it's kind of obvious that I will use exactly the same technique for 8. I will divide, so for n is equal to 8, what I will have is, I will have x1 plus etc. plus x8 divided by 8. That's my beginning on the left, right? All 8 numbers. I don't want to write each one of them. But then I can pair them, and I will have x1 plus x2 divided by 2, plus x3 plus x4 divided by 2, etc. x7 plus x8 divided by 2. And then divide by 4. Well, probably let me just write down all 4 components. Would be nicer. So next one will be x5 plus x6 divided by 2, and next will be x7 plus x8 divided by 2. So obviously, the average, arithmetic average of 8 numbers can be represented as average of 4 numbers where each one is a pair average of the previous 2. Okay, now, but this is the same as this, because I can just consider these as separate numbers. And if I will use this previous theorem for n is equal to 4, I can say that this is greater or equal than 4th root of their product, right? x1 plus x2 divided by 2, x3 plus x4 divided by 2, x5 plus x6 divided by 2, and x7 plus x8 divided by 2. So here we were using this one. Now, again, let's use the same theorem for a pair. So instead of x1 plus x2, I can reduce it even further, so it will be square root of x1, x2. Same thing here, here, and here, so basically it will be greater or equal than 4th root of 2 roots, which means it's the 8 roots of their product. And that's exactly what we had to prove. So, as you see, we are relatively easily going from 2 to 4, from 4 to 8. So, my first step in the proof of the original theorem for any number n would be not a transformation from n equals k to n equals k plus 1. I really don't know how to do it easily. Instead, I will transform it from n is equal to 2 to the k's power to 2 to the k plus 1's power. So, from 2 to 4, from 4 to 8, 2 to the 3rd power, from 8 to 16, 2 to the 4th power, etc. Now, I will prove this as a separate step in the whole theorem, in the whole proof of the whole theorem. Now, so I'll have, instead of having every number, I have 2, 4, 8, 16, etc. Now, how about 3? How about 5, 6, and 7? How about 9, 10, etc.? Well, this will be the second step of the theorem, of the proof. Instead of going forward, now since I have any big number basically at my disposal where the theorem is already proved in the first step, I will go backwards. Apparently to go backwards is easy. So my second step in the proof will be, if the theorem is equal for n is equal to k, then it's equal for n is equal to k minus 1. So, again, it's a very important difference from the traditional one-step proof, from k to k plus 1. I will do it in 2 steps. First, for n is equal to 2 in the kth degree to k plus 1. That's how I will get my big numbers. And then, in the second step, I will prove that from any number I can go backwards. And that's how I will cover all the steps. How, for instance, I can get to number 9? Well, very simply. The theorem was proven for 2. Using this, I can therefore say that it's true for 4, and for 8, and for 16. Then, if it's true for 16 using the second step, I will go backwards to 15, 14, 13, etc. to 9. So that's why the combination of these two steps basically completes the proof for any number. Alright, so we have the plan. We know more or less how to prove this one. I'll just repeat the same thing I did like 2, 4, and 8. And then this will be a separate step. So, step number 1. Right, before, whatever I was talking before was just a preliminary kind of explanation of why I have chosen to do it this way. And you're obviously welcome to try to do it in a classical mode, like from k to k plus 1. Personally, I found it extremely difficult. I just wasn't able to prove it that way. So maybe there is no good proof. So anyway, you're welcome to try if you want to. But in any case, if you would like to follow this particular plan, which definitely I recommend this one, this is a good point in time to place the pause button. Try to do it yourself, and obviously this one you have already basically seen in a couple of examples how to do that. And as far as the next step, I can give you a hint. To transform from k to k minus 1 is relatively easy. If you know that for k it's true, but you have to prove that it's true for k minus 1, you just have to add extra number to these k minus 1, and so you will get the k numbers, and they will not tell you which number to add. That's kind of up to you. But this is just a little hint. In any case, I will do both steps right now without any interruptions. So go ahead, press the pause, think about it, and then turn it back up on again, and we'll continue with the proof. Okay. Now, let's consider the theorem is true for n is equal to 2 to the kth degree, and we have to prove that it is true for 2 to the k plus 1. Well, very easily. Since now I have x1 plus x2 plus etc. plus x2 to the k plus 1. I hope I relatively big numbers, big letters, so you will see. And we divide by their numbers. And obviously, to prove that this is greater than their geometric average, I will separate pairs of these numbers. Now, if total number of my numbers is 2 to the power of k plus 1, and if I pair them, how many pairs do I have? Well, obviously, I have to divide the total number of numbers by 2, since every 2 elements will give me a pair. Now, if I will divide 2 to the k plus 1 by 2, obviously I will have 2 to the kth degree, the power of 2 to the power of k. So, if I will do it like this, divided by 2 plus x3 plus x4 2 to the 2 plus etc. plus my 2 last elements will be x with an index 2 to the power of k plus 1 minus 1 plus x with an index of 2 to the power of k plus 1. That's my last pair. It's a little bit difficult on indexing here, so it's x with an index of 2 to the power of k plus 1 and then minus 1, because this is the previous member. And the last member is x with an index of 2 to the power of k plus 1. So, how many pairs, as I said, 2 to the power of k? So if I divided 2 to the power of k, that's what we will have. Now, in this particular case, so far, this is not greater or equal, this is just straight equal. So all I did, I separated into pairs, divided each pair by 2. So now I have to divide by 2 to the k's, and altogether will be this 2 will go down, so with 2 times 2 to the k's, it will be 2 to the k plus 1, exactly what we have in the beginning. So that's how we reduce the number of elements from 2 to the power of k plus 1 to the number of elements 2 to the power of k. Now, since we have assumed that our theorem is true for number of elements equal to 2 to the power of k, I will use it here right now, and I can say that this is greater or equal than their geometric average. Now, the geometric average is, the number of elements is 2 to the power of k root, same number as here, so this is 2 to the power of k. And under this root, I have their product, which is x1 plus x2 divided by 2 times x3 plus x4 divided by 2, etc. And the last member is, again, this kind of a difficult to write, x with an index 2 to the power of k plus 1 minus 1 plus x with an index of 2 to the power of k plus 1 and divided by 2 the whole thing. Okay, so that's what we have. And obviously now we put even greater than even more. Now, since our theorem is proven for n is equal to 2, each arithmetic average of a pair I will replace with their geometric average. So I will have the same 2 to the power of k root, and here I have a square root of x1 times x2 times again square root of x3 times x4, etc. And the last root, square root, will be product of x with an index of 2 to the power of k plus 1 minus 1 times k with an index of 2 to the power of k plus 1. Okay, that's my last square root, and this is my 2 to the power of k root. Well, and now it's basically obvious. If you multiply all these square roots, you can have only one square root from everything. And if you will have a square root and then root of and degree with a degree of 2 to the power of k, obviously the result will be 2 to the power of k plus 1, root of their product. And the last one is x with an index of 2 to the power of k plus 1, which is exactly what we needed to prove. So from k, 2 to the power of k, we can always step forward to the next element, the element 2 to the power of k plus 1. So that's basically the first step of the proof. Since it's true for n is equal to 2, it's true for 4, for 8, for 16, for 32, for 64, etc., etc. We double and double the number of elements, and that's how we can move forward in bigger and bigger steps to get the points where we have already proven our theorem. Now let's talk about the second step, how to move backwards, and from, let's say, 16 we can go backwards to 15, or from 32 we can move backwards to 31 and then 30 and 29, let's say. And that would complete the whole proof for any number. So let's assume that the theorem is true for n is equal to k, and we have to prove it from k to switch to k minus 1. Okay, so for n is equal to k, we assume it's true. And we have to prove it for n is equal to k minus 1. All right, so let's have k minus 1 elements divided by k minus 1. All right. Here is an interesting thing. It's kind of obvious that if you have an average of certain number of elements, arithmetic average, and then you have one extra number which is exactly equal to their average, the whole combination shouldn't really be different as far as the average is concerned from the one before. So what I'm saying is that if I have an average of k minus 1, let's call it 1. And now let's have an average of k elements, which are original k minus 1 plus their average y. And I have an average of k elements now. Original k minus 1 plus their arithmetic average, but now I divide it by k. I would like to say that it's very obvious that we should really think about this combination as really not being different as far as its average is concerned from the original one. And how to prove it? Well, let's just open up this thing and check if we will go and we will be reduced to the same formula as before. So what this is x1 plus x2 plus x3 plus etc. plus xk minus 1 plus. Now y is again x1 plus x2 plus etc. k minus 1 divided by k minus 1 and divided by k, right? That's what it is. Okay, now we will use k minus 1 and multiply it by each of those guys to bring them with the common denominator k minus 1. So what is this? Well, it's x1 will be k minus 1. Okay, we will put k minus 1 down and this k. Now x1 will be with k minus 1 plus k minus 1 I will multiply for x2 plus etc. plus k minus 1 we will multiply by xk minus 1 plus all these guys. So plus x1 plus x2 plus etc. xk minus 1. Right? So x1 was k minus 1 here, and 1x1 is here, from here. So altogether will be k times x1. Same thing for x2. We have k minus 1 times x2 and plus another x2. So it's k again, kx2. As you understand, it will be exactly the same thing for everyone up to k minus 1. And we divide by k minus 1, k. And obviously you reduce it by k, and you have arithmetic average of k minus 1. So this is a proof that adding arithmetic average of k minus 1 numbers does not change an average of a set. If it was y, it will be exactly the same y at the end. So adding average to a set of numbers does not change the average of the combined set. This is a very important property, and we will definitely use this in this particular case. Since we have just proven that average of k minus 1 numbers and average of k numbers, previous k minus 1 plus their average, is exactly the same thing, then we will do the following. I have to prove that this arithmetic average of k minus 1 is greater than their geometric average. But since I know that this thing is the same as x1 plus x2 plus etc. plus xk minus 1 plus their average, and average by k, since I have just proved that, now I will work with this. But now this is an average of k elements, right? And I can use an assumption which I had. Because we started from, let's assume that it's true for n equals k, and then let's just move to k minus 1. Okay, but k minus 1 I can actually represent as an average of k numbers, original k minus 1 plus their average. And this, we can use our assumption for n is equal to k and say that this is greater than k's root of x1, x2, xk minus 1, and what is this? This is k minus 1 root. Well, let me do it in two steps. x1 plus x2, etc., xk minus 1 divided by k. Okay. This is the product of from 1 to k minus 1, and the kth component is, k minus 1, is their arithmetic average. Now, it would be a little easier for me if I will use, instead of roots, I will use the powers. You know that eighth root of b is basically b to the power of 1 over 8. It's just easier to work with. So I will have it as x1 times x2 times, just do it here, x1 times x2 times etc. times x1 plus x2 plus xk minus 1 to k minus 1, and the whole thing is in the power of 1 over k. Okay, now you see, here is a very important thing. This component is exactly equal to this component. So, what I will do, I will just transfer this space into this using basically the regular transformation. Because this is equal to, since this is a power and this is a product, I can separate the components, so it will be x1, x2, etc., xk minus 1 to the power 1 over k times x1 plus x2 plus etc. plus xk minus 1, k minus 1 to the power 1 over k. So this is inequality which I have. This piece is greater or equal than this piece. Let me just write it again so it would be a little easier to understand what I have done here. Greater or equal than this. I'll just rewrite it. x1 times x2, xk minus 1, 1 over k, x1 plus x2 plus xk minus 1 divided by k minus 1 to the power of 1 over k. So that's what I have proven, meanwhile. So, what I'm saying is that this member, you see, looks like this member. So, what can we do about this? Well, first of all, we will raise both left and right to the power of k. What will be is x1 plus x2 plus etc. plus xk minus 1 that's plus 2k minus 1 to the power of k greater or equal. Now, if I will raise to the power of k these guys, the powers are multiplying, so that will be x1, x2, xk minus 1. 1 over k to the power of k will be 1, so it will be just this. And same thing here. Uh, 1 over k to the power of k will be the same thing. And now I can obviously reduce by this number. I will put this and k minus 1 here, right? That's the reduction. And this is basically the end of the proof, because now we will just have the k minus 1's root from both sides of equation, of an equation, and we will get what we want. Greater or equal k minus 1's root of their product. And that's what we had to prove. So again, what we have done here, how to switch from assumption that it's true for n equals k to prove that that would be true for n is equal to k minus 1. To k minus 1 original elements, I added the kth element, which is their arithmetic average. And since it doesn't change the whole arithmetic average, now we have k elements, original k minus 1 plus their average, arithmetic average, and I have applied the formula, the inequality for n equals k, which we have assumed is true. And then it's just pure arithmetic reduction, power here, power there, that's just very simple. So that completes the proof of the whole theorem. Again, it's attributed to a French mathematician Cauchy, and it was actually a very interesting theorem about this comparison between arithmetic and geometric averages of two sets of numbers. Now, there are many averages, and by the way, in finance, if you're interested, all these averages are used quite substantially. Let me just talk a little bit about something which is called moving average. Now, moving average is a concept very often used in the finance when you are analyzing stock market quotes or something like that. Here it is. If you have, let's say, the value of Dow Jones Industrial at the end of every day for, I don't know, like a few years history. So you have date number 1, industrial average had the value of x1. Day number 2, it has the value of x2, etc. And you have day, I don't know, 3000, let's say. And industrial had x3000. What is moving average? Moving average is the following. If this is today, the date number 3000, what we can say is, okay, what's the average of Dow Jones Industrial during the last 100 days? Well, you should really add together x3000 plus 2009,999, 2009,998, etc. So you go backwards by whatever number of days I decided to have my average. Let's say it's by 100 days. Okay, so this would be G 290001. Okay, so x2901. So we are averaging these numbers, and this constitute my average. Let's call it Y3000. This is an average of the last 100 days as of today. Okay, great. What was it yesterday? Well, yesterday I had to add from x 2900 to x 20999, right? Yesterday it was 2999, and the 100 days before it was this. So this constitutes y 2999 of 100 days. So for every day, for today, which is 3000, or yesterday, which is 2999, or the day before, which was 2998, we can have the average of the previous 100 days. Now, these numbers constitute another sequence. It's the sequence of averages. So if x were sequence of values, y is sequence of their moving averages, where average is calculated always for the last 100 days. So that's basically something which, again, financial specialists are using every day to analyze how certain indices or certain stocks or certain markets, whatever, or currencies, for instance, exchange rates, how they behave. What do they accomplish? Well, obviously, every individual day can represent certain haptic movement, up, down, etc. But if you're averaging throughout, let's say, 100 days or something like that, you are smoothing the curve. So if originally a daily graph would be something like this, your moving average graph would be much more smoother, something like this. And it represents bigger waves, so to speak. If these are daily waves, then averaging by the last, whatever, 5, 10, or 100 days, you are smoothing out all these daily fluctuations, and only the bigger waves are actually staying in this particular graph. So it's just one of the examples of how averages are used in finance. Obviously, they're used everywhere for statistical purposes, etc. But again, what's interesting is that even in finance, if you are saying average, okay, but which average? Arithmetic average or geometric average? And there are other averages like quadratic average, for instance, which we might actually have another problem about. So all these are important, and as you see, if you use arithmetic average, it's always greater or equal than geometric average. Okay, that completes for this problem for today. There is one interesting detail, actually, I would like to mention for those who are interested in these arithmetic averages or geometric averages. This inequality which we have, that arithmetic average is always greater or equal than geometric average, I said it's always greater or equal. Now, the question is, when is it greater or when is it equal? Well, interesting point is that if you will take only 2, now obviously the equal sign will be if they are equal to itself. If both are the same, x plus x divided by 2 will be x, x times x will be x squared, and the root will be again x. So if x1 is equal to x2, this is equality, and the interesting thing is that for any number of elements, equality will only be in case when they're all equal to each other. And I'm not going to prove that. Try to prove it yourself. That's an interesting problem. Thank you very much. Enjoy it. Hi, I'm Zor. Welcome to Unizor Education. I would like to present one more problem on induction, mathematical induction, just to prove one more formula. It's a good exercise, and probably it will just demonstrate one more time how the induction approach helps you to prove certain formula. And the formula by itself is very helpful. I'm sure we will use it throughout our algebra course in many different ways, whenever it's appropriate. So, well, here it is. What I would like to proof is the formula we can represent the difference between two powers. N is an integer number, obviously natural number, greater than 2 or equal to 2. And the representation of this is a minus b multiplied by a sum of products of a to certain power and b. What's interesting here is I'm decreasing the powers of a and I increasing the powers of b. So a is decreasing from a to the n minus 1 to a to the power of 0. That's why there is no a here. It's 1. It's constant. And b is increasing from b to the power of 0 to b to the power of n minus 1. So in this sum, every element, every product of a to some power and b to some power has a sum of powers always equal to n minus 1, which makes the whole multivariate polynomial, as this is called. In this case, it's two variables, a and b, and it's polynomial because it's a sum of a and b multiplied in certain powers. So it makes the power of every element to be equal to n minus 1, which is always a sum of powers, a to the m times a to the n, or rather b to the n. This element always has a power of m plus n. So the power of every element in this sum is equal to n minus 1. So it's n minus 1 and b to the power of 0, n minus 2 and b to the power of 1. So again, the sum is n minus 1, etc. So the whole polynomial is of the power n minus 1. This is polynomial of also multivariate polynomial of the power of 1. And when we multiply two polynomials, again, the powers are added together. So 1 and n minus 1 gives you n. And that's exactly what's the power of this particular polynomial. So everything fits. But now we have to prove this formula, and I'm going to prove it by induction. So first what we do, we check it for beginning value, which is n is equal to 2. Well, if n is equal to 1, doesn't really make much sense. We don't really have it. It's already a minus b. So starting from n minus 2, what will it be? It will be a squared minus b squared on the left. On the right, this is a minus b times, so this is a polynomial of the power of n minus 1. N is equal to 2, so it's just 1, which means a to the power of 1 times b to the power of 0. And then the last one. Now, there is no n minus 2. These are all non-existent things. Only the last one will be present, which is b. And this is a known formula. I mean, if you don't believe that this a squared minus b squared equals to a minus b plus times a plus b, let's just multiply. It's equal to a minus b times a plus a minus b times b, which is a squared minus ab plus ab minus b squared, ab minus and plus a squared minus b squared, what's necessary to do. So n is equal to 2 is fine. Now, the next step is we assume that this formula is correct for some n is equal to k, which means we assume that a to the power of k minus b to the power of k is equal to a minus b times a to the power of k minus 1 plus a k minus 2b plus etc. plus a b k minus 2 plus b k minus 1. So we assume this is correct. And now let's substitute n k plus 1. So we have to do a k plus 1 minus b to the k plus 1. Okay, what will that be? Well, how can it be proven using this? Well, let's think about. So we know that this is true. So why don't we do this? Yeah, I think it would work. Let's do it this way. I subtract a to the case b and add a to the case b minus b to the k plus 1. Right? I don't change this. I added a minus a to the power of k times b and plus a to the power plus b. All right. It's equal to, well, we can factor out a to the power of k. From a to the power of k plus 1, we still have a left. A to the k's, and a would be exactly a to the k plus first. And from there, it would be minus b, since I factor out a to the power of k. Here, I will factor out b. So it will be plus b, a to the power of k, minus b to the power of k. Okay, why did I do it? Well, because this is something which I already assumed can be represented as this sum. So let's do it. So I leave this one without any change. Now, this I will represent as a minus b times this sum. A k minus 1 plus a k minus 2 b plus etc. plus a b k minus 2 and b k minus 1. Okay. Now, as you understand, I can factor out a minus b from both sides, from both terms, right? So it will be a minus b, and what will be left? A to the power of k plus b multiplied by all this. So a to the power of k minus 1b, a k minus 1b. Then we are decreasing a and we increasing b. b and b squared, a to the k minus 2, etc. And two last members will be a b k minus 1 plus b k. Lo and behold, this is exactly what this, what did I write here? I'm sorry. This is not. Yeah, I didn't really write my expression. Okay, but this is exactly expression of this kind. This is exactly expression of this kind with n is equal to k plus 1. Look at this. This formula with n equals to k plus 1 should be a to the k plus 1 minus b to the k plus 1, which is what I have started with, equals to a minus b, which is this. Now, instead of n, I should substitute k plus 1. So it will be a to the power of k. That's a to the power of k. Then a to the power of k plus 1 minus 2, which is minus 1 times b, which is exactly this, etc. My power of the a is decreasing, and the power of the b is increasing, until the last one, b to the power of n minus 1, where n is equal to k plus 1, is k, right? b to the power of k. And that's exactly what we have. So, by doing this manipulation, I have proven that assuming that this is correct for n is equal to k, and I'm explicitly using it here, from here to here, I substituted from there, from this expression, the whole expression, which I have assumed is correct. I have come to the same formula for n is equal to k plus 1, which basically concludes the proof. So this formula is quite useful, actually. You can have some examples of this. Let's do a couple of examples of this formula. And you don't have to really remember every example as long as you remember the principle that if you have a difference between two powers, then you have the difference between the bases, and then times the very symmetrical polynomial of two variables, which is multivariate polynomial, with the power, which is basically this power minus 1, with gradually decreasing the first component and increasing the second component as we move along the sum towards the end. So, in case of a square minus b square, we already know this is a minus b times a plus b. This is probably everybody remembers by heart. Well, with the cube, it's a little bit more complex. Now, the polynomial should be of the second degree, right? Because this is the third degree. This is the polynomial of the first degree, so this is supposed to be a polynomial of second degree, which is a squared plus we're decreasing a and increasing b. So after 2, I go with the power of 1. After b to the zeroth power, I have b to the first power, and b squared. And that's basically the formula. Similarly, a to the fourth minus b to the fourth is equal to a minus b times. Now we have to have a polynomial of the third degree, right? Because this is fourth, this is 1, this is the first degree, so this is supposed to be third degree. So we start from a to the third, and we will finish with the b to the third, but we're decreasing a and increasing b. So you got the picture. Well, that's it for today. Thank you very much. That was problem number 7 of induction. Thank you.